Okay, section 1.2 is reflections and stretches. So yesterday all we talked about was horizontal and vertical translations, right? So that was moving left or right, up or down. Okay, so today we're talking about stretches and reflections. So a reflection means it's going to make the image reflect onto the other side or reflect down. Okay, and a stretch means it's going to make it taller or it's going to make it wider across the x-axis. Okay, so on our notes it says you might want to highlight the dotted area. It's y equals, and if you have a negative in front of the f of x, hold on, I get my pen going. So if I have negative f of x, that means that this is a reflection on the x-axis, but it's changing the values of y. Okay, so this is a reflection. So this guy right there, that negative sign, that's a reflection on the x-axis. And I know that sounds like the opposite of what it is because it's affecting the y's, but all that means is your y values are changing and your x is the mirror. So when it says a reflection on the x-axis, it's meaning your x is the mirror and then it's reflecting your points, okay? So reflection on the x-axis, and we'll just say changes y values to opposite sign. Okay, so if they were negative before, now they're positive. If they were positive before, now they're negative. Okay, so that's how a reflection works. If we had a reflection and it was inside with our x, that means that's a reflection on the y-axis. And that's going to be changing our x values. Because remember, anything in the bracket is affecting our x's, right? So we call this one a reflection on y-axis. And it changes our x values to opposite. Okay, so if they were negative before, now they're positive. Okay, so our first example, it says compare the graphs of f of x, y equals negative f of x, and y equals f negative x. Okay, so it says given the graph, so we're given the original f of x graph right there. It says graph this one, and then we need to graph the second one when it's a reflection on the x. So the easiest way to do this, remember, is we get a table, we'll mark down what our points are, and then we'll change the points, and then we'll graph. Okay? So I'll make my table. This is for my original picture. My original picture has the points marked on it, so I just have to find out. It's -4 and -3. Then it looks like it's -2 and -3. This one is, where are we at here? 1 and 0. This one right here is 3 and 4. And then our last point, E, is 5 and -4. Okay, so there's our x and y table. Okay, now if we want to find this reflection, this is a reflection on the x-axis, meaning we're going to change all our y's. So this new table, nothing's going to happen to our x's. Nothing's happening with them, so we just write them how they are. Okay, what happened? -4, -2, 1, 3, and 5. And then what's happening is, since a reflection on the x, because the negative sign is outside, that means it's going to change our y values. So any value here, oops, I started to erase them. Any value here is going to be of the opposite sign. So if this was -3, now it's 3. -3, 3. 0 has no sign, so it's just 0. 4 is now -4, and this -4 is now a 4. Okay, so then if we were graphing that, I wonder if we can fit it on this table. It would be, maybe I can even change my pen color. Let's see how. Okay, so this would be -4 and 3 up would be a point. It would be -2 and 3. Okay, and then it would be 1 and 0. 1 and 0. 3 and -4. And then 5 and 4. So 5 over 4. Okay, so that would be our reflection. All it did was take our picture and flip it upside down. Okay, so if you notice on these two graphs, did you notice these points? They showed up on both of the pictures because changing the sign to 0 doesn't change anything. Okay, this point, and if you flip your page, it has the definition, it's an invariant point. So an invariant point is a point that once you've did some sort of transformation and you still have the exact same point and it's a shared point on both graphs, those are invariant points. So this guy here, this 1 and 0, he's an invariant point because his sign did not change and he shows up on both of the pictures. So that's the definition of an invariant point. We can also do the table for if we were doing the reflection on the y-axis. Okay, so our we go back to our original, so don't get our tables mixed up. Go back to the original points. So our y points should be staying the same as our original. And then our x points change to the opposite sign because this is a reflection on the y-axis, so our x points change to opposite sign. So if we had -4, this is now 4. It was -2, so it's 2. We have a -1, a 3, sorry, a -3, and a -5. Okay, and then we would just graph those the same as we did the last ones. I don't have really much room to do it, but that's what we'd be doing. Okay. Okay, so we flipped the page. We talked about invariant points, remember? So those are the points that stay the same when you transform. Let's look for example 2. Okay, here we go. We have example 2 in our notes. This is the part that bothers me, I think, that the writing stays. Okay, so it says, given the graph, we have a graph of y equals f of x. We want to transform the graph of f of x to g of x, describe the transformation, state any invariant points, state the domain and range. Okay. So, let me just erase all this. So g of x is now our new equation. Okay? And, oh yeah, before we get into this, I guess we need to talk about stretches and compressions. Okay, so in our notes before we do example 2, it talks about stretches and compressions. I'll try to add a blank page here. Okay, there we go. Okay, say we have this. A is representing a value that's in front. Okay, so remember, if A is negative, that's a reflection, right? If A is negative, that's a reflection. So A has like two pieces. If it's negative, it's a reflection. We don't want to forget that. There would be a reflection on the x axis, which changes your y's. Okay, so if this guy is negative, there's a reflection on the x-axis. That's what we just talked about on the last page. Also, A represents a stretch. Okay, so before when we used to teach it as a stretch or a compression, meaning it either makes it bigger or it squishes it. Okay, now they just call it a stretch even if it squishes it. Okay, so if A is like 2, let's say an example, if A is a whole number, then it's going to make it twice as big. Okay, if A is a fraction like half, you're cutting all your y's in half. So it's a whole number. Multiply your y's by whatever A is. Okay, so if A is 5, that means all your y values are now 5 times what they were before. Okay, if A is a third, now you're timesing all your y values by a third, which just means you're dividing them all by 3. Okay? I guess it doesn't even have to be a whole number. That works for any of them, right? If it's a whole number or a fraction, you're still multiplying. You just have to remember if it's a half, you're timesing by half or dividing by 2 is the same thing. Okay? So this one, these are called vertical stretches because they affect our y points. Okay, they make our picture either taller or shorter. Okay. Then we have these situations where our value is in with x. Okay, so remember when we had a translation in there, if it was negative, it actually was like positive to the right, and if it was positive, you actually went backwards to the left. Everything in the x bracket seems to be the opposite. Same works here. Okay, so if you have a half as your b value, that means your x's are all going to be twice as big. Okay, so before, if you had a half here, you cut all your, if we were talking vertical, there we go. If we were talking a vertical stretch, if it was a half, you cut your points in half. When we're talking a horizontal stretch like this, the opposite happens. So if, I'll just do an example. If b is a half, multiply your x's, so all your x values, by 2. Okay, so that means if your b is 2, you're actually cutting your x pieces in half. Okay, so it works the opposite way as the vertical stretch. So this is a horizontal stretch, sorry. So if b, let's just say, is 3, then you multiply your x values by a third, or divide by 3 is the same thing. Okay, so that one in the brackets works the opposite of the vertical stretches. Okay, are we okay with that? We'll move to example 2. Okay, so I don't know why that does that. Okay, number 2. Okay, so again, we were talking about these equations. So it says you're given the new equation. We have to describe the transformation. So that just is say what is happening. Okay? So in this A question, we have g of x is equal to f of x. So what is that? What do we call that? A vertical stretch of 2, right? So that just means all our y values are going to multiply by 2. Okay, then it says state any invariant points. So it's probably best if we graph the picture first and then state the domain and range. Okay, so if we were doing this, let's just describe this one. Sorry, what's this for B then? Vertical stretch of a half. So that would mean all your y values are just cut in half. Okay, so if I was listing my points for the original picture, I'll make my table, and my points were, I was at -6 and 4, so my points are -6 and 4, -2 and 0, 0 and 2, 2 and 0, and 6 and 4. Okay, those are my points that make up that W shape. Okay, so now if I'm doing the stretched version, that means my y points are all going to be 2 times as big. So that just means I multiply all my y points by 2. Okay, so my new table, sorry, and I don't have a whole lot of room. Okay, so my new table for this graph here is going to be -6, and now this is 8, -2 and 0, 0 and 2, or sorry, 0 and 4. And then 2 and 0, and then 6 and 8. Okay, so all I did was multiply all my y points by 2. Okay, the other question said, what are the invariant points? So those are the points that didn't change between the two graphs. So this one was -2 and 0. This one is still -2 and 0. This one was 2 and 0. This one is still 2 and 0. So this one has 2 invariant points. Okay. So if we wanted to graph this, sorry, I'll move back here. If we're graphing this, we're going to graph the new points on this graph. So this was -6 and now 8. So we're here. And then we're at -2 and 0. So that's our invariant point. It's shared. And then we're at 0 and 2. No, what are we at? 0 and 4. And then 2 and 0, another invariant point. And then we were at 6 and 8. So if I drew this, my new picture looks like this. Okay. And the last piece says state the domain and range. So if I was talking the domain for the original picture, I'll maybe put that in blue since the original picture is blue. Okay, the domain means how far it goes left to right, right? So this blue picture goes from -6 all the way to 6. So my x's have to be greater than minus 6, but they have to be less than 6. And my range, it doesn't go into the negatives, but it goes, the highest it goes is 4. So your y has to be greater than 0, but less than 4. And I'll switch back to a red pen. If we were doing the domain for our new graph, then ours goes as far as minus 6, right? The domain doesn't seem to change because it goes as far as 6, so it will be exactly the same. Our range, though, goes all the way to 8 now. So it was lowest as 0, and it goes as high as 8. Okay, I'm not going to do this example here because it's done exactly the same way. It's just you're cutting the y pieces in half. Okay, also we have example 3, which is very similar to the example we just did. I'll just go over it briefly because it's just affecting our x pieces instead of our y. Uh-oh. Come back. What did I do last time to make it? You guys remember? What's that? It just came back on? Okay. Whew. Okay, so example 3 is like very similar question. Oh, that drives me crazy. I need tech support, you guys. What's that? Yeah. So same question, except we're doing horizontal stretches now. Okay, so we're not going to do all the same work again because it's very similar. It's done the same, but we'll just talk about the difference here. So I know it's a horizontal stretch because my value is with my x. Okay, so in this situation, we would say this is a horizontal stretch of a half, because remember, the opposite happens. So in this situation, we'd be taking all our x values and cutting them in half. Okay, in this situation, it's a horizontal stretch of 2, meaning all of my x values are multiplied by 2. It's the opposite of what's happening when it's in the brackets. Okay, so I think that's all we're going to talk about with that because it's done exactly the same way. We would write out our points, and this time we'd be changing our x values, not our y values. Okay, so your picture is going to either shrink this way or stretch that way this time. Okay. Okay, and then our last example. It's example 4. Okay, so this is saying, and sorry, yours didn't print in color, but it labels which is f of x and which is g of x. So it says the graphs here have been transformed by either a stretch or a reflection. Write the equation of the transformation. Okay, so this is the original equation. F of x equals absolute value of x. Okay, and what we need to know is what happened to this one. Can we tell by just looking at it? Yeah, it looks like it's getting taller. So my guess is a vertical stretch, right? But we don't know by how much. Okay, so what we can do is we can pick out some of the points on this graph. So wherever it's hitting perfectly, right, you can label those points. See here. And then we can label the other ones and check them out. So here's our points. Come on, there we go. These are our points. I have a minus 6 and 6, minus 4 and 4, minus 2 and 2, 0, 0, 2, 2. They keep going like 4, 4, 6, 6. Okay, so then if I had my other points, if you notice, you hit the ones that are perfect on the lines. Okay, that table, the x's are not changing, but our y's are minus 6 and we're at 18, minus 4 and 12, 0 and 0, or sorry, minus 2 and 6, I missed one, and 0 and 0, and then 2 and 6. Okay, so we noticed nothing happened to our x's, so this is a vertical stretch. It's affecting our y's. And how much did it stretch it? It went from 6 to 18, 4 to 12, 2 to 6. Yeah, by 3. So our new equation would actually be like that, 3 times as big. Okay, and if we look at this graph here, is this a stretch or a reflection? Reflection. Who is the mirror in this? The x-axis or the y-axis? The x-axis is acting as a mirror. So that means our y values are the ones that should be changing, right? Okay, so if we wrote, so if our original equation is this, and we just said it's a reflection on the x-axis, which means our y's change. A reflection on the x-axis looks like this, right? It has a negative in front. Yeah, we could write the points out on the table and check it out and see, and we'd find the same thing.